In this video, I want to talk about a third example of eigenvalues and eigenvectors for 3 by 3 matrices. So in this example, we're going to talk about the matrix A, which is 3, 2, negative 1, 0, 4, 1, 0, 0, 4. And what I want to do is I want to remind you of something that we discussed previously, but I also want to just point out, so let's just do it. So let's look at A minus lambda I. A minus lambda I is going to be 3 minus lambda 2, negative 1, 0, 4 minus lambda 1, 0, 0, 4 minus lambda. So there's going to be a few things that happen in this example. But what we're going to do is we're going to look at the characteristic polynomial, set that equal to 0. And the characteristic polynomial is just the determinant of A minus lambda I. And that's going to be 3 minus lambda times 4 minus lambda times 4 minus lambda. So we know how to find the determinant very quickly. In triangular matrices or even diagonal matrices, you can just take the product of the diagonals. And so that tells you that if this is going to be 0, then we have two eigenvalues, 3 and 4. 3 is an eigenvalue of multiplicity 1. So this is multiplicity 1. And 4 is an eigenvalue of multiplicity 2, because this is 4 minus lambda squared. So just as a reminder about multiplicity, because this is a new concept, 3 is a solution of multiplicity 1 because you have a hidden 1 there. And 4 is a solution of multiplicity 2 because you have a power of 2 there. And so what we're going to do then is let's look at the eigenspaces for each of these eigenvalues. So let's start if lambda is equal to 3. This is a multiplicity 1 eigenvalue. That means that the eigenspace will have dimension at most 1. And what we're going to do then is let's look at A minus 3i. And we're going to solve this for x. In other words, this is the null space of the matrix A minus 3i. And so what we're going to do is this, I like to think of these as just solving these augmented matrices where you have the matrix A minus 3i augmented with the 0 matrix. A minus 3i is just going to be 3 minus lambda, 4 minus lambda, and 4 minus lambda when lambda is 3. So this is going to be 0, 2, 1, 0. I'm just reading off columns now. And then negative 1, 1, 1. And it turns out that this is, you can check that you can add multiples of row 3 to row 1 and row 2 to make those two terms go away. And then you can add a multiple of row 2 to row 0 to make that term go away. Put everything in a nice order. You end up with 0, 1, 0, 0, 0, 1, 0, 0, 0. And so if I wanted to study the solution here, what would happen is notice that we have x3 is 0, x2 is 0, x2 is 0, and x1 is free to be whatever we want it to be. So x1 is t. That means that the eigenspace E sub 3 is going to be the set of vectors t, 0, 0, where t is a real number. In other words, the span of the vector 1, 0, 0. 1, 0, 0 being that vector I hat, the standard basis vector in the x direction. Anyway, so that's E3. That's the eigenspace there. And if lambda is equal to 4, then we're going to do the same thing, and A minus 4i times x equals 0 is going to lead us to solve the augmented equation A minus 4i augmented with 0. And A minus 4i is just going to be negative 1 to negative 1, 0, 0, 1, 0, 0, 0. I'm just taking A minus I and plugging in lambda equals 4. So you get negative 1, 2, negative 1, 0, 0, 1, 0, 0, 0. All right. And when you simplify this, do some row operations, you'll end up with eventually the matrix 0, 0, 1. Again, that cancels off that term. So now you have negative 1, 2, and I'm just going to put the negative there, switch the sign. So this will be 1, negative 2, 0, and then a row of zeros. And so our solution is going to be that x3 is 0. x2 is then going to be the value that we parameterized by, so x2 will be t. x1 then will be 2t. And it turns out that if you look at e sub 4, this is going to be all the multiples of this value, all the values 2t, t0, where t is in R. In other words, the span of the vector 2, 1, 0. So it turns out that in this case, the dimension of the eigenspace E4 was just 1, even though 4 had multiplicity 2 in the characteristic equation p of lambda equals 0. So the dimension of the eigenspace is always less than or equal to the multiplicity. In this case, it's strictly less than the multiplicity, and that's going to happen. Okay, but it's worth seeing an example where that happens. We'll see where the dimension of the eigenspace and the multiplicity being different leads to problems down the road.